Hey, seventh grade, welcome back. This is your lecture on light and sound. So go ahead and get the Google Slides pulled up if you do not have them already. Take a moment and do that. Your warm up says, which is faster, the speed of light or the speed of sound? And you may already know this answer. I'll give you a second. Here's my little dance for you to pause the video if you don't know. Okay, if you guessed light, you're right. Yay! So the speed of light can be measured at almost 300,000 kilometers per second. That's a lot. It could circle the Earth 7.5 times in 1 second. Really fast. It takes a single bit of sunlight 8 minutes and 20 seconds to reach Earth. So the sun that you're looking up at outside, one bit of light takes a whole 8 minutes to get to you. The speed of sound in comparison is still pretty fast, but not nearly as fast as the speed of light. It's only about 343 meters per second. That's meters, not kilometers. So that's about just over, I don't know, 100 meters is roughly equal to a football field, if not a bit less. So like 3 football fields in a second. It's fast. Yeah. So if you go to slide 3, we have our definition of light, and the very technical definition I put there. It says light or visible light is electromagnetic radiation within the portion of the electromagnetic spectrum that can be perceived by the human eye. That, I'm sure, made absolutely no sense to you, so I parsed through that and put the easy definition. So visible light is what we can see, what the human eye can see. And this visible light is a type of wave in the whole electromagnetic spectrum. So remember, electromagnetic waves are what makes up this spectrum. The spectrum ranges from a low frequency all the way up to a high frequency. And this spectrum, again, is made of electromagnetic waves. It's actually a form of radiation. That what is light is made of. Light is just energy. Okay? Light is energy. Visible light is what we can see. So if you move to slide 4, there is a copy of the electromagnetic spectrum there. So you'll see on the left are gamma rays. And on the right are radio waves, like AM, FM, in your car, on your clock radio, whatever. In the middle, you'll see that rainbow. That's visible light. That's what we humans can see. Other organisms can see different ranges of light, but the visible light for humans is somewhere in the middle, okay? So anything that's outside that little range, we can't see, but we'll be able to measure it. We know it's there. Gamma rays, if you are a comic book buff, gamma rays are what Hulk was hit with and turned him into the Hulk. It's what hit Bruce Banner, and now he's the Hulk. Gamma rays are extreme radiation, very dangerous. X-rays, they're a type of wave that, yes, that's how you get your x-rays at the doctor's office. Of course, we use them safely. It's only very small amounts, and it's all medically safe. But they are what images your bones, so they can see what you broke. You've heard of UV and infrared light. We use them to see different things like heat signatures and all that. And radio waves, I know this may sound kind of weird. Radio waves are a form of light, not sound. They carry sound, but they're not a sound wave, they're a light wave. So if you look at that little rainbow, you'll see in the center is green. Fun fact, green is the easiest color for the human eye to see. So that's why if you've ever seen night vision goggles, everything's green, because the human eye can pick up the most shades of green. Fun fact for the day. So if you go to slide 5, I talk about waves. Waves are made of energy, as I said, and they're measured in nanometers. Remember nano, your prefix. It is 1/1000th of a meter, so it's like really tiny, that's why we can't see it. The smaller the measurement, the higher the frequency, and thus the larger the measurement, the lower the frequency. So if you look at that little clip from the last picture, you'll see on the left, 400 nanometers is on the left, and its waves are really tight together. They're more frequent, okay? So it's a higher frequency because they occur more often. They're shorter waves, shorter space between the waves. If you go over to the right and you see the 700 nanometer, it gets longer. The space between the waves is larger. It is a lower frequency because instead of going like this, it goes like this. Okay, if you can track my finger fast enough. Lower frequency because it occurs less often. So moving from waves into the next slide on sound. Sound is a vibration or a wave that travels through matter, whether it's a solid, liquid, or gas, and can be heard. All right? Sound moves through objects. It needs the molecules of an object to vibrate in order to carry sound. So let's think of playing the guitar. You start the sound wave by plucking the string, and the air molecules that it starts traveling through, they vibrate and carry the sound. The type of matter very much affects how sound travels. Interestingly enough, sound travels faster in water than air. And through air, sound travels about 1 mile in 5 seconds. So if you ever heard that old story, if you hear a thunderstorm but it's not where you are yet, and if you can hear the thunderclaps, you count seconds between how many, like between each clap of thunder. That's how far away it is. It's because it takes that long to travel to you, and you can tell, like let's say there were about 7 seconds between each thunderclap, it's probably about 7 miles away. So get inside because the thunderstorm's heading your way. All right, slide 7, about sound waves. Just like light, sound's made of waves, all those curvy little lines. So the difference is that the higher the pitch of the sound means the higher the frequency. Shorter waves, they're closer together. So if I have a pitch that's here, do, and a pitch that's here, do, the higher one, higher frequency. A note that volume is independent of frequency. So if you have some music and you turn it up, your frequency hasn't changed. Okay. Now all the different pitches that are happening in the music, that's a different frequency. But let's say we just play a salad sound because we can. If you turn the volume up or down, it's not going to change frequency. It's all related to pitch. You'll see in the picture there, the lower pitch has the longer waves. They're more spaced out, and the higher pitch has the shorter waves. They're closer together. An interesting thing about sound waves is that you've probably heard of this before, the Doppler effect. So you can probably hear the Doppler effect as I move closer to the screen. So the frequency is the same, the pitch is the same, the volume can be the same, but because sound moves, when a sound gets closer to you, it sounds like it's louder, but it's not. So if I am talking like this and I lean away and I keep talking at the same volume, but then I get closer, it's going to sound louder. That's a Doppler effect. There's a lot more physics to it, but fun fact. It's because the frequency stays the same, the waves stay the same, but it's all in relation to position. All right. So your homework, there's a couple questions. Just email them to me. They should be pretty easy to understand, so do some research. Where are microwaves on the electromagnetic spectrum? Tell me about one of these light waves I told you about, all that. There's some sound questions as well. Have a good day. Spring break's almost here. We got this. Yay, bye.